How to prevent thermal runaway in batteries. Abstract. This document outlines practical actions to prevent thermal runaway in batteries, a critical safety concern in various applications, including electric vehicles and energy storage systems. By focusing on robust thermal management, safer battery materials, safe storage and charging practices, and additional safety measures, we can significantly reduce the risk of thermal runaway incidents. The following sections provide a detailed breakdown of these key points. 1. Robust thermal management. Active cooling. Liquid cooling, essential for high-power applications such as electric vehicles and large energy storage systems. This method circulates coolant to effectively remove heat from the battery. Forced air cooling utilizes fans to move air across battery surfaces, helping to dissipate heat. Passive cooling. Heat sinks, metal components designed to absorb and dissipate heat from the battery. Phase change materials, PCMs. These materials absorb heat by changing state, e.g., from solid to liquid, providing effective thermal management. Heat pipes efficiently transfer heat away from the battery, enhancing cooling performance. Ventilation. Design battery enclosures with adequate airflow to prevent heat buildup. Ensure that vents are not blocked to maintain proper air circulation. Thermal insulation. Use materials such as ceramic blankets or aerogels to isolate battery cells and prevent heat transfer. 2. Safer battery materials. Electrolyte modifications. Solid-state electrolytes, emerging technology that is inherently less flammable compared to traditional liquid electrolytes. Additives. Incorporate additives into liquid electrolytes to reduce flammability. Separator improvements. Ceramic-coated separators enhance thermal stability and reduce the risk of thermal runaway. Shutdown separators. These separators melt and block ion flow when overheated, preventing further temperature rise. Cathode and anode materials. Utilize more thermally stable cathode chemistries. Select materials that are less prone to dendrite formation, which can lead to short circuits. 3. Safe storage and charging practices. Temperature control. Store batteries in cool, dry places to avoid extreme temperatures that can trigger thermal runaway. Charging management. Implement a high-quality battery management system, BMS, to monitor and control charging. Avoid overcharging or deep discharging batteries to maintain their health. Use chargers specifically designed for the battery type to ensure compatibility and safety. Cooling during charging. Ensure adequate ventilation during charging to dissipate heat. Allow batteries to cool after use before initiating the charging process. Battery replacement. Regularly inspect batteries for signs of damage, such as swelling or cracks. Replace batteries that show signs of degradation to prevent potential hazards. 4. Additional safety measures. Cell balancing. A BMS should include cell balancing functionality to ensure even charge distribution among cells. Rigorous testing. Conduct abuse testing, overcharge, short circuit, crush, in controlled environments to assess battery resilience. Perform thermal testing to determine the limits of the cells. Regular inspections. Visually inspect batteries for any signs of damage or wear. Monitor battery performance, including voltage and temperature, to detect any anomalies. Implement regular maintenance schedules to ensure ongoing safety. Practical tips. For consumer electronics, always use reputable brands and chargers to minimize risks. For electric vehicles and large energy storage systems, rely on professionally designed and installed systems to ensure safety. Educate users about safe battery handling and charging practices to promote awareness. Follow the battery manufacturer's guidelines for optimal safety and performance. By implementing these strategies, we can significantly mitigate the risks associated with thermal runaway in batteries, ensuring safer usage across various applications.